Okay, so we're going to be doing chapter 19 next. So this one is going to be talking about carbonyl compounds, and so specifically aldehydes and ketones and the reactions of those. So with any new class of compounds, right, we're going to talk about naming. So for the aldehydes and ketones, it's actually pretty straightforward. So with the with aldehydes, right, so you're going to need to find the longest chain, right? But it has to contain the aldehyde within it, right? With the aldehyde, right, with the longest chain, we're going to take off the E at the end and replace it with the suffix al. So for al for aldehyde. So from there, you're going to find the side chains, get the numbers, right? So the aldehyde's always going to be carbon 1. So that makes the numbering of the chain pretty easy. But then that also means you don't need to put a number in front of the main chain with the aldehyde in it, because we always assume that it's going to be number 1 So since the aldehyde has to be at the end. And then you just put the side chains in alphabetical order, right? And put the parent chain at the end, right? So if we've got something like this, so we have this, right? So I put in the dots for the carbons, right? So 1, 2, 3, 4, 5, 6, right? So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, right? So our main chain is going to look like. Let's go up there. It's not going to make a difference, right? So since it's 2, 3, 4, 5, 6, right? So it's C6, right? So normally that would be a hexane, right? I'm going to take off the E and add an Al. So it becomes hexanal. So okay. So here's our side chains. We have that methyl group, that methyl. So methyl. Right, so the aldehyde's always going to be carbon 1, right? So we go 1, 2, 3, 4, 5, 6, right? So we have a methyl at 4, right? Methyl at 5, right? So our final name is going to be 4,5-dimethyl hexanal. Right? We have a main chain that's 6 long. Oh, hey, we also have an aldehyde in it. That's going to be carbon 1. We have 2 methyl groups, right? Where are they? One's at carbon 4. One's hanging off of carbon 4. One's hanging off of carbon 5. There you go. Not too bad. Now for ketones, it's going to be very similar. So you're going to have to find the parent chain with that ketone group in it, right? So and here, instead of, you take off the E, and then instead of doing the al for the aldehyde, right? It's going to be O and E, right? So people know this. Right, so if you have acetone, that's a ketone. So it's easy to remember. So you're going to find the name, the side chains, right? So and then determine the numbering. Now you're going to have to tell me where that ketone group is, right? So this is very similar to when we had the alkenes and alkynes, things like that. You got to tell me where that is, right? So is it a 2 ketone, a 3 ketone, whatever, something like that. So. And then you assemble a name. You put the ketone number right in front of that main chain name. So okay, so here we go. Right. So here we go. All right, put the you always put your dots in like that, right? So here's our main chain, right? So we gotta figure that out, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So it's looking like it's 8, right? So here's your main chain, like that. Now, carbon 1 is going to be very similar to where the double, right? When we were naming alkenes, it's going to be the end that's closest to the ketone. That's going to be carbon 1. So here's your ketone, so that means this one's going to be carbon 1, right? So here we go. 1, 2, 3, 4, 5, 6, 7, 8, right? Like that. So here we go for our side chains, right? So methyl, that methyl, oops, and then these two methyl groups, right? Methyl, methyl. Okay, so we have, right? So we did the numbering. Oh, and then we also have to include the where the ketone is, right? So put that in quotes. So here we go. So we have a this methyl group at 2, that one at 6, that one at 7, that one at 8, right? And with that, and then the ketones at 3. Okay. So here we go. So 2, 6, 7. Oh, so not 7. Sorry, that's a 7, not an 8. This one's at 7, not 8. So 2, 6, 7, 7. Tetra, meaning we have, right? So we have 4 tetramethyl. 3. Oh, we never did that. We never did the main chain, right? So C8, that would be octane, right? But since it's a ketone, we're going to take off the E and write octanone, right? So it'd be 3-octanone. So there we go, right? So this is why, right? So for that, so if you have tetramethyl, right? So for that, you got to put all the 4 numbers in there, right? So if I were to just write 2, 6, 7 tetramethyl, I wouldn't know where that 4th one is. Is it on the? Is an extra one at the 2, extra one at the 6, extra one at the 7, right? So for that, so you got to tell me where all those methyl groups are specifically, right? So what do we have, right? We have a main chain that's 8 long, right? It has a ketone in it, the O and E, right? Where is it? It's hanging off of carbon 3. Oh, hey, we have 4 methyl groups. Where? Right, so we have 4 methyl groups. Where are they? Right, one's hanging off of carbon 2, the other one's hanging off of carbon 6, and then we have 2 of them hanging off of carbon 7. So there you go. Now you can also have cyclic ketones, right? Like that. Now, again, you're going to have the main chain. It's got to contain the it's got to contain that ketone group in it, right? So it's going to be this the ring here, right? So remember, it's always either ring or straight chain. You can't do both, right? So our main chain is going to be this, right? So, right, so it'd be C5, right, which would normally be pentane, right? But we've got, it's a ring, so we have to say cyclopentane. Cyclopent, right? And then we're going to take off the E and put O and E there. So it's a cyclopentanone. That's the main chain. Now, for rings, where you know the question is always carbon 1. Oh, let's do the side chain, right? So we could do the ketone. You don't have to put it in there, but it's never a horrible idea. Right? So we have this methyl group here, right? And then we also have that ethyl group, right? You don't necessarily need to put the ketone in there. We always know that that's going to be 1, okay? And so if we're going to go clockwise, right, so it'd be 1, 2, 3, 4, 5, right? So the ketone would be 1, this would be 2, and this would be 3, right? If we were going to do counterclockwise, right, it'd be 1, 2, 3, 4, 5, right? So that would mean that the ethyl group's at 4, the methyl's at 5, and this is again at 1. So you add them up, right? So it'd be 6, 10, right? So we're going to take those numbers, right? So it'd be, right? So which comes first, ethyl or methyl? Ethyl comes first, so it'd be 3 ethyl, right? 2 methyl, 1 cyclopentanone. Now, you could also have it so that you could just say 3 methyl, 2 ethyl, 2 methyl cyclopentanone. You don't necessarily have to put that 1 in there. So here I don't put it. You can do it either way. I'm going to count it right either way. Stuff like that. So, but if you want to keep it straight, you can go ahead and put it in there. But the acetyl bond O is always going to be, right, the ketone is always going to be carbon 1 in that ring. Okay, next up is what if you have an aldehyde and a ketone in your compound? Okay, so with that, so the priority goes to the aldehyde. Okay, it's going to be the more reactive of the two, so it gets the priority. With that, so I don't know why you can't see those the slides here. Let me turn this down. That's a little bit easier. Oh. There you go. It's a little bit easier to see. Okay. So with aldehydes and ketones, the aldehydes actually get the priority, and the ketone group is labeled oxo, so it's considered more like a side chain, right? So it's considered oxo. So here we go. So if we have this compound, we're going to name this just like we would any other aldehyde. It's just we have an oxo side chain. Okay, so here's our side chain, right? So 1, 2, 3, 4, 5, 6, right? Or don't forget 1, 2, 3, 4, right? Or we could do 1, 2, 3, 4, 5, 6, 7. But what's the rule? Right? We have to include the aldehyde in the main chain. So even though we have one that's longer, this does not include the aldehyde. So we need to include this in there. So this is going to be the main chain here, right? So the aldehyde, right? So it's 1, 2, 3, 4, 5, 6. So it's C6, which is normally hexane, right? But since it's an aldehyde, it's a hexanal. Okay. Now, our side chains are going to be this ethyl group here, right? And then that group there, which is an oxo. Okay. And again, with aldehydes, right? This is going to be carbon 1, right? So it's going to be 1, 2, 3, 4, 5, 6, right? We don't have to include the aldehyde in there. We know it's going to be 1. So with right, so the aldehyde's 1, right? So the ethyl's hanging off of carbon 2. This one's hanging off of carbon 3. Right? So which one's first alphabetically? The ethyl is, right? So it's going to be 2 ethyl, 3 oxo, hexanal. There you go. A little bit easier for you guys to see. Okay. Next up. Okay, so how do we prepare them? Now, they're not the easiest things. Aldehydes, in particular, are not the easiest thing to prepare, and stuff like that. And so what's going to happen is we're going to get there in 2 different ways. We're going to learn some other ones. We have learned some other ones, but one of the ones we're going to learn about today is doing oxidations and reductions. Okay, and so one of the more common methods of doing this, right, so with that, is to take a primary alcohol here like this and oxidizing it with Des-Martin to form this. Okay, Des-Martin pyridinate, that's the compound there. I'm just going to call it Des-Martin. That's what everybody calls it. With that, but you can notice an oxidation, right? Because if you look here, there you have 1 carbon-oxygen bond, right, and 2 carbon-hydrogen, right? And what happens here is that you burn one of these carbon-hydrogen bonds and turn it into a carbon-oxygen bond, right? So because here, right, you have 2 carbon-oxygen and 1 carbon-hydrogen. This is an oxidation. Right? So we can go from a primary alcohol to an aldehyde, right? Des-Martin, it goes up 1 step, right? Or you can go down. You can reduce it. Okay, so if you're going to take, you have the ester here, right? You have what's called dibol. Now I think the book calls it dibol. It's diisobutyl aluminum hydride. Dibol is probably more correct. Nobody calls it that. Everybody calls it dibol. something like that. And so what you do is you say, okay, here, right, notice how there's 3 carbon-oxygen bonds, right, and 0 carbon-hydrogen. What's going to happen for a reduction with dibol is you convert one of these carbon-oxygen bonds down to a carbon-hydrogen. And how do we do that? So what does that mean? So the product's going to be 2 carbon-oxygens and 1 carbon-hydrogen. How does that work? That's going to be an aldehyde. So to like that. Okay, so this is a reduction. And then this part goes away. So the cyclopentyl group here, that goes away from the ester. Okay, so Des Martin's going to click it, convert one of your carbon hydrogens into a carbon oxygen, or you can take dibol, which converts again one of your carbon oxygens back to one of your carbon hydrogens. So you can either go up 1 carbon oxygen bond, or you can go down 1 carbon oxygen. Okay, so like that. So to make ketones, right? So remember you have to have carbons on either side, but again, the easiest way to do this is probably do oxidizing, right? So with that, so if you look at right there, right, there's a hydrogen here, right? So 1 carbon hydrogen, right, 1 carbon oxygen. If you hit this with chromium trioxide or permanganate, potassium permanganate, so with that, so you can get this here. You're going to convert this guy into here. You convert all of them actually, and so now that carbon has 0 carbon hydrogen bonds and 2 carbon oxygen bonds, right? But a ketone. Okay. Another way that we learned this back last semester is to do ozonolysis, right? So like that. So ozone, do zinc acid workup, right? So remember these guys here, it's a molecular chain saw. It cuts that in half, and so you get oxygens on either side, right? So you're going to get these 2 products, but notice how they're both ketones. Like that. Now, if there was a hydrogen here, right, you would make the aldehyde version. So, okay. Another nice way of doing aromatic ketones, right? So with that, we learned about this previous chapter, right? Doing the acylation, right? So chlorine, right? So you can do this Friedel-Crafts, so aluminum chloride, right? So you're going to put the benzene is going to go where the chlorine is, okay? So with that, so you're going to make between this benzene and here, because that's where the benzene is, or that's where the chlorine is attached. So you're going to make this, but notice how this is, again, it's ketone, right? So it's a nice way of doing aromatic ketones. So one of the things that can happen, okay, with aldehydes is that they can. So when you're doing this, and this will be apparent here. Notice for all of those previous ones, right, how we're taking we're just interested in the carbons that have the oxygens attached. We're taking carbon hydrogens and turning them into carbon oxygen bonds. So as long as this carbon where the oxygens are has carbon hydrogen bonds, we can increase the number of carbon oxygen bonds. Okay, so if we have, right, so if we have this, right, we can oxidize, right? So there we have two carbon oxygen bonds, right? 1 carbon hydrogen. So if we're going to oxidize, right, we're going to take one of these and convert it into that. And so we know that the product's going to have 3 carbon oxygen bonds and 0 carbon hydrogens, right? So it would be great if we could do, single, double, it'd be great if we could do that, but that doesn't exist. I mean, that's carbon monoxide, stuff like that, but we're not making carbon monoxide. So the way that we have to do this is we have to do a carboxylic acid, right? So that carbon there, right, it has 1, 2, 3 carbon oxygen bonds, no carbon-hydrogen bonds, just right there. Now it does have a hydrogen on it, right? But that's an oxygen-hydrogen bond. That's different. So you're just looking at the carbon-oxygen, carbon-hydrogen bonds. Stuff like that. So okay, stuff like that. So because what's going to happen is, right? So with primary alcohols, right? Right, they're going to look like this, CH2, right? When you do the oxidation, right? So you're going to go from, at that carbon, right? You're going to have 2 carbon hydrogens, right? 1 carbon oxygen, right? So to oxidize it, right? One of those is going to get converted into that. So you know what the product's going to look like, right? So it's going to have 1 carbon hydrogen, 2 carbon oxygen, right? So how are we going to do that? Well, that's an aldehyde, right? But we still have this carbon hydrogen here, right? So we can convert, again, we can convert another one in there. So now there's no carbon hydrogens, 3 carbon oxygens. Stuff like that. So, like that. So, so like that. So now, right? So we've burned all of these, right? So how do we do 3 carbon oxygen bonds, right? We make the carboxylic acid. Okay, so for primary alcohols, right, we can put that, we can oxidize those all the way up to the carboxylic acid. With secondary alcohols, okay, I can spell, right? So they're going to look like, going to look like this, and right there's a hydrogen, right? So that carbon there is going to have, right, 1 carbon hydrogen bond and 1 carbon oxygen, right? So when we oxidize, right, so one of those is going to get converted. So we know what the product's going to look like. It's going to look like, it's going to have no carbon hydrogen, 2 carbon oxygen, right? So our product's going to look like that. But since we're out of carbon hydrogen bonds, right, we can't go any further. So if you have a secondary alcohol, it's going to stop at the ketone. Primary alcohols can go all the way up, right, because we have enough carbon hydrogen bonds to take, to convert. Here we only have 1. Now with tertiary alcohols, right, they look like this. Okay, this guy here, it has 1 carbon oxygen bonds, but it has no carbon hydrogen. So it has no currency to be able to do any further oxidation. So tertiary alcohols, you're not going to get any oxidation. So no oxidation on these guys. Okay, so as long as you have carbon hydrogen, and it's just where that oxygen is. Where that oxygen, it activates these carbon hydrogen bonds, allows them to be oxidized. As long as you have them there, you're good to go. And you burn them until you stop. Okay, but for tertiary alcohols, you don't have any, so they're resistant to oxidation. Okay, so if we look at this, chromium trioxide, right? So what do we have, right? So remember we have a hydrogen there, right? So that has 1 carbon hydrogen bond there and 1 carbon oxygen, right? So therefore we're going to convert these. So chromium trioxide converts them all. So our final product is going to have 0 carbon hydrogens, 2 carbon oxygens, right? So we can predict what it is. So it's going to look like that. Right, this product, right? So right there, right? That's the corresponding oxygen or carbon here. That's not going to have any carbon hydrogens, but 2 carbon oxygens. Okay. Now the next one, right? Sometimes it's good to put right in the hydrogens, right? Because we're interested in that carbon there. Now for Des Martin, right? This only goes one step. Okay, chromium trioxide goes the whole way, but Des Martin only converts 1 at a time. Okay, so here we have 2 carbon hydrogen, one carbon oxygen, right? So with Des-Martin, we only convert one. Here we convert them all. Up there, the chromium trioxide, we would convert them all. Here we only convert one. So we can predict what our final product is going to be. It's going to have one carbon-hydrogen bond and two carbon oxygens, right? So our product is going to look like this. And look like that there. So Des-Martin only goes one step. Chromium goes all. Okay. Now for Dibol, again, for this, right? So for Dibol, it's one step down. Okay. So we're interested in that one, right, where the oxygens are, right? So that has no carbon-hydrogen bonds, but it has 3 carbon-oxygen. And so what's going to happen is we're going to convert one of those to a carbon-hydrogen. So you can predict what's going to happen, right? So it's 1 carbon-hydrogen, 3 carbon-oxygen. Oops, excuse me, 2 carbon-oxygen, right? So our product's going to look like this. Right, so right there, you have 1 carbon-hydrogen, 2 carbon-oxygens. There you go. Okay, so for reactions with these C double bond, they're all going to take advantage of the fact that the C double bond O, okay, with this bond here, right? So this is the oxygen's more electronegative because it's nearer to fluorine on the periodic table. That's going to have negative character. That's going to have positive character. Okay, and so if you have any sort of nucleophile around, right? Right, this guy's going to attack here, right? It's going to attack that carbon, and since we're making a new bond, it's going to have to force this guy up here, stuff like that. And so what you're going to get is, let's say you had something simple like this, acetone, right? And then you had your nucleophile, whatever's attacking. Right? This is going to attack here. This is going to get pushed up. Now during the workup, this is going to become an alcohol. Right? So this is the intermediate, right? Right, so let me put in the lone pairs here. Right, so this double bond becomes an extra set of lone pairs, right? So you get your nucleophile. This is called the tetrahedral intermediate. Tetrahedral intermediate, right? And then during the workup, this gets a hydrogen, so you end up with something like this. So you end up with this case where you have whatever is attacking plus the alcohol, right? So this oxygen here becomes this is this oxygen here, and then your nucleophile attack. Nucleophile is hanging off of it. Okay, and so it doesn't necessarily matter if this is a ketone. Aldehydes can do the exact same thing, right? So like that. So it's going to look like this. Now this can further degrade, okay, stuff like that. But this is going to be what you're looking for here. Okay. Now in general, so this is a nice multiple choice question, right? So for the general reactivity of these things, regular aldehydes are going to be, so alkyl aldehydes are going to be the most reactive, right, compared to ketones. If these things are hanging off of a benzene, right, these guys are going to be further reduced. So it's aldehyde ketone. It's basically what the trend is. But regular alkyl aldehydes and ketones are going to be more reactive than their benzene cousins. Okay, so it has to do with it. You can sort of think about this being at the sort of a primary. It says one carbon versus secondary, right? So this is going to be more reactive. Now the thing with the aldehydes is, if you were to get this intermediate, right? So you get the stabilization. The aromatic aldehydes and ketones, like these, there's a lot of stabilization that happens, and so this thing, so it's what's going to happen is essentially you're going to have this is going to have less positive character because any sort of positive charge that could be on this carbon is going to be reduced because that charge can get resonated around the ring, stuff like that. So stuff like that. So water is a nucleophile, okay, and stuff like that. So you're going to see this. You're going to get really sick of this by the end, okay. So what's going to happen, sort of generally, right? So if we have this here, we're going to have water come in and attack, right? Push that up. So you're going to have a water plus what attacked it. Now, one of these hydrogens is going to go away, so like that. But essentially, it's going to be water plus what attacked it. Now, for ketones, this is pretty slow. So if you have a bottle of acetone, it's pretty much just going to be acetone. But if you have a bottle of formaldehyde and you put in a little water, it's almost always going to be completely hydrated, right? And this is owing to the reactivity of ketones versus aldehydes. Okay, so this one here, where you have two alcohols hanging off the same carbon, this is what's called a gem diol or a geminal diol, right? So Gemini, right? The twins. So but that's so this is the right. So that's what that's called. So with that, so we're going to talk a little bit about the mechanism of these things, right? So with that, so if you have just acetaldehyde here, which is this, okay, what's going to happen is we're going to have water, right? So we'll put that there, plus a little bit of catalytic base. Okay, so this is catalytic. So we're going to have to regenerate that. Okay, but again, remember, so we're going to end up making this, right? And with the OH down here, right? So by that, we're going to make an alcohol. This is an OH plus what attacked it. Okay, so by that, so here the mechanism, it turns out it's this, right? Because we have partial positive, partial negative, right? So it's actually the base that comes in and attacks it and pushes that up. So you end up with this, the tetrahedral intermediate, right? I should put the lone pairs up here for the mechanism, right? But here we go. Here's the OH, right? Now here, remember, the best to think of the water, this water here, is HOH, right? So this guy here just comes in, rips off the water, pushes that there. So you end up with this plus OH minus, right? You regenerate your catalyst. That's not too bad, right? So it does. So this coming in attack, pushing that up, okay, to make what attacked it, and the O minus, the tetrahedral intermediate. Now this comes in and rips off a hydrogen to regenerate your base catalyst. Not too bad. Problem comes when you can also do the same reaction but with the acid. Now the problem with this is we can't have any formal negative charges, right? Because as soon as we do, what's going to happen is your acid catalyst is going to get gobbled up. Okay, but you end up making the same product. It's just the mechanism is a little bit different. That. Okay. Okay, so for here, what's actually going to happen is, remember, we always think of water not as H2O, but rather HOH. Okay, and so here, you're going to kind of turn things around a little bit, because now here is the positive charge and here's the negative. Okay, and so what ends up happening is this ends up, oh, no, I'm sorry, not to that point yet. This is attracted to that. Okay, we can have positive charges around, right? So this is going to have negative character, right? Negative, positive. Negative character is going to attack that to make this. Right? Okay. Now a nice resonance structure of this is this, right? Because we have an oxygen with a positive charge, something electronegative with a positive charge. So you could do this resonance structure like that. Now, I'm sorry, now this guy can come in, attack there to make this okay. So you made the water, or the OH plus what attacked it, right? But since this is positive, we're going to have another water come in. Grab that. You end up with this plus H3O plus, which is just your acid catalyst. So basically what you're having to do is rejigger this thing so that you only have positive formal charges on here. But essentially you're going through the same intermediate, right? This OH with what attacked it. Okay. Now the rest of these are going to follow that same course, right? So like that. So you're going to end up with, right? So if you have benzaldehyde here, right, plus HCN, right? So this is negative, positive, right? Negative, oops, positive, negative, right? So this is going to attack there, push that up. This is actually going to rip off that hydrogen too. So you're going to end up with, and you'll see this trend, OH, H, right? On that, where the C double bond O was, it turns into an OH plus what attacked it. Okay, this is what's called a cyanohydrin. Okay, now this we can actually take, right, because this is a CN, right? So a CN is actually a C triple bond N, right? So this is CN, right? So if we take this and reduce it, right? Okay, so we can turn that triple bond into double bonds by adding hydrogens to it, and so what ends up happening is you end up with right, so there's the C, there's the N, but what we end up doing is put hydrogens on it. Okay. So now we've made a new carbon-carbon bond, right? So that's the nice thing about making the cyanohydrin. We've made a new carbon-carbon bond. Now the other thing that we can do is we could add. Actually, this should be water, H plus, H2O, and heat, and decompose that to the carboxylic acid. So OH. C, but now what we're going to do is we're going to convert this carbon here into a carboxylic acid. Okay, so these oxygens come from the water, right? So like that, and so you make a nice carboxylic acid. Plus, I guess you plus NH4 plus. Okay. Okay. So for a hydride, okay, you're going to do the exact same reaction. Right? We can't add sodium NaH. That's actually a really crappy nucleophile. And so what we do is we add sodium borohydride, right? But essentially this is just a H minus source, okay? And so again, you're going to get an attack there. You're going to kick this up, so you're going to end up with this. OH plus what you attacked with, which in this case is just an H. Okay, it doesn't matter if it's an aldehyde or ketone, it's going to work the same way. Okay, an OH plus what you attacked with. And here's the mechanism, right? So you're going to attacking here, right? So to make the tetrahedral intermediate, and then during the workup, which you dump in water, you end up making the alcohol. Okay, so for Grignards, right? So these are carbon compounds. So these are carbanions, right? So if you had this, right? So if you had something simple like ethyl Grignard, right? So CH3, CH2, MgBr, right? So remember this where this is attached, that's a minus. So that's going to attack there, kick that up. So you're going to end up with, as always, the OH plus what you attacked with, CH2, CH3. Right? Now the mechanism is a little weird, but the product is what you're interested in. Again, it's this OH plus what attacked it. Okay, so predict the products. Okay, so here we go. Okay, again, these are going to be, now this is a bad mechanism, so, but again, it's attack, kick up, right? So it's going to be OH on this carbon here, right? It's going to be an OH plus, right? Plus what attacked it, which is the water. Okay, so this oxygen is that oxygen, this oxygen is that oxygen. Okay. So for this one, right, plus, so this is 1, 2, 3, 4 carbons long, so CH2, 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 CH3, right, so MgBr, right, so this has a negative charge on it, right, because the MgBr, right, so the Mg is going to be +2, so you need that minus there, right, so this is going to attack there, kick that up, so what you're going to end up with is on that carbon, right, an OH plus what attacked it, CH2, CH2, CH3, CH2, CH3, right, so that attacks there, kicks this away to end up with an alcohol. Okay, notice the theme here. Okay, so we have CH3, right? Now this is actually a two-parter, okay? So HCN, right? So I'm going to do the first part, HCN, right? Again, the CN is going to attack there, kick this up, OH, CH3, plus what attacked it. Okay, now the second part is this lithium aluminum hydride. You're going to have to know that that converts that triple bond here into single bonds. Okay, so it ends up being OH, CH3. Now down here, this is going to be CH2 and H2. Converts the CN triple bond into just adding, reduces it down to a single bond by adding hydrogens across it. Okay, but remember this intermediate step, right? So this first step gives you just the normal stuff. Okay? Now the last one, right? So remember sodium borohydride, right? So that's just H minus. Okay. Again, you're going to get attacked there. That's going to kick up. So you're going to end up with OH plus what attacked it. Okay? There you go. Okay, now nitrogen compounds become a little bit more complicated. They do the same stuff, but they decompose after you make it, because what you're going to release is water. Okay, so let me talk about the mechanism. Okay, so if you have a primary amine, so an NH2 with something hanging off of it, what happens when you react with the C double bond O, you end up with this what's called an imine, so carbon-nitrogen double bond. Okay, if you act with this tertiary amine, or secondary amine, where you have two things hanging off it, just a single NH, you're gonna form what's called an enamine. So the ene, right, would be the double bond here, and then an amine. Okay, so it's gonna react off to the side, or you're gonna make this double bond off to the side, and stuff like that. And so the mechanism is here. Okay, so the mechanism is a little complicated, but it's not too bad. The first thing that happens, right, the amine attacks here, kicks this up, so you end up with what would be the alcohol plus what attacked it, carbonylamine intermediate, just what we normally would expect. But what ends up happening is there's still, because you had a little bit of acid catalyst, this thing is going to eventually rip off, you're going to release water, and then it's going to decompose to the enamine. So these two compounds are actually the same thing. It's just this has been you've just rotated around this bond. Okay, but the easiest way to think about this is to say, okay, we're going to need a double bond in here somewhere. Okay, so we have this here plus CH3 NH2. Okay, so what's the product, right? So we throw in a little bit of acid catalyst. Okay, so if you count how many, so nitrogen hydrogen bonds here, so if there's two here, okay, that means that our product is going to have two carbon nitrogens in it. If we have two nitrogen hydrogen bonds, that means we're going to have two carbon nitrogen bonds in our product. Okay, so what's the easiest way to do that? Like this. Okay, and then this CH3 group just comes along for the ride. That's the easiest way to think about this. With the secondary amines, we're just going to do the acetophenone here, but it's going to work the same if it's well, it's not, but right. So with that, but so here, let's say we have this dimethylamine, right? So we only have one nitrogen hydrogen bond, so that means our product can only have one carbon nitrogen bond. Since we have to have a double bond in our product, that means that this one has to have, you're going to end up needing to have a carbon double bond, stuff like that. So our product is going to look like this. Right, we can only have, because we only had one nitrogen hydrogen bond here, that means we can only have one carbon nitrogen bond here. So that means the double bond has to go off to the side. Like that. Okay. Okay, so for the rest of these, right, so these are the two that we just learned. Okay, these two are exactly the same thing as this guy here. It's just all you're doing is replacing the CH3 with something else. Okay, in this case, right? So if you have an O8, if instead of the CH3, you know, this could be any chain, by the way. It doesn't have to be methyl. It could be a cyclopropyl. It could be whatever. Stuff like that. So this guy here, in this case, the OH is coming along, right? So instead of this case, there's a methyl group coming along for the ride. In this case, there's an OH coming along for the ride. Okay, so that makes this compound, this group is called an oxime. Okay, so here, right, so you still have the primary amine, right, because you have an NH2, but in this case it's connected through another nitrogen, and this primary amine is going to be more reactive than the secondary amine, but it's still just this group here coming along for the ride. Okay, and so you end up with the hydrazone here. Okay, so with that, but these two reactions are basically no different than this reaction here. It's just you're replacing, in this case, the CH3 with something else, but it's the exact same thing. Okay, so predict the products. Okay, so here we go. Okay, so you're going to dump in a little bit of acid catalyst. Okay, so we have two nitrogen hydrogen bonds, so that means our product is going to have two carbon nitrogen bonds. Okay, so the easiest way to do that right? So is to make it like that. And 1, 2, 3, 1, 2, 3, right? So we have 3 carbons on it. There. Now I don't care if it's this way or that way. I don't care. Okay, so like that, but it's going to need to look similar to that. Okay, we're going to put the nitrogen. You're going to supplant the this nitrogen for that oxygen. You're just going to bolt that in, replace it right there. Oh yeah, there's also water that comes along. It's not a big deal. So this oxygen ends up going onto this water here. These two hydrogens end up being those 2 hydrogens there. Okay. So next up, we have that. We have this. Right. Actually, we're going to need a little bit of acid catalyst here. Right. So again, this nitrogen is going to supplant that hydrogen. But the problem is, right, so we only have 1 nitrogen-hydrogen bond, right? So that means our product can only have 1 carbon-nitrogen bond there, right? So it's going to need to go off to the side, okay? Oop, that should just be a single bond, right? The double bond is going to have to go off to the side, okay? Now, you could technically get 2 products. You could get a double bond going on this side or the double bond going on this side. This is probably going to be the major product, right? Because we don't like having nitrogens at the end, right? So like that. So this is probably going to be the major product here. Okay. Now last up, we have this acetophenone plus the NH2OH, right? Maybe dump in a little acid catalyst. Right, this nitrogen is going to supplant that, right? But we have 2 nitrogen-hydrogen bonds, right? So that means we're going to have, we can get out 2 carbon-nitrogen bonds at the end, right? So we're going to make our normal like that, and then this OH coming along for the ride. Now again, it doesn't matter if it's this side or this side. You're not to that level yet. Okay, so there we go. Now, Wolff-Kishner. Okay, now this is the easiest reaction you're going to learn. Okay, what it does is it actually removes the oxygen out of the reaction and replaces it with 2 hydrogens. Okay, so like that. So the easiest way to do this, okay, and it doesn't matter if it's an aldehyde or a ketone, it works the same way. Okay, so if we have acetophenone here. Right, Wolff-Kishner, so NH2, NH2, KOH. Okay, those are the reaction conditions. Okay, the easiest way to think about this is to rewrite your original molecule. This works better when it's a skeletal structure. Actually, let me do that. When it's a full skeletal structure. Just redraw it as a skeletal, and then just erase that part there. That's your structure. Okay. So if you're going to do this, Wolff-Kishner, NH2, NH2. Right. Again, you just redraw it and then just erase the C double bond out. That's it. Okay. Okay, so predict the products for this, right? Okay. Now, what's happening is, I forgot to mention, there are hydrogens going there, but the nice thing about skeletal structures is you don't have to draw them, so there you go. But this one, if you were to draw it out, would be, I forgot to say that, would be CH2, CH3. Right, this one would be 1, 2, 3, 4, 5, right? So it would be CH3, CH2, 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 CH3. Okay, so that's actually what's going on. But doing skeletal structures is nice, right? Do that, and then just erase that there. Okay, we have that, right? So Wolff-Kishner, NH2, NH2. redraw the molecule, and just erase that. That's it. Okay, now for the acetal. Okay, so we, if you took the course earlier, okay, so this is chapter 25. We're actually introducing these, and it turns out with the carbohydrates, and so what you end up having is if you mix acetyl bond O with, say, an alcohol, so CH3OH, what ends up happening is you throw in a little bit of acid. What happens is, again, you get this attacking there, putting up, so you get the you get the alcohol displacing here, OH plus what attacks, but that actually happens a second time, and so what you end up with, because the molecule can release water, you end up with this. So this oxygen ends up leaving as a water, and you get a replacement of the carbon-oxygen bonds with, again, ether bonds, which are just carbon-oxygen bonds with the alcohol. Okay, stuff like that. And so what ends up happening is, if you look at this mechanism, you end up coming down here. So this is the normal stuff we've seen, right? So you end up with an OH plus what attacks you, right? And so instead of getting the full, right, so you just have the OH on this side and the alcohol on this side, which, you know, this ends up being with what attacked it on this side. That ends up what's called a hemiacetal, or a half acetal. Okay, but what ends up happening is that OH ends up leaving as water, and then another alcohol molecule can come in and attack. I should say that there's two here. Another alcohol can come in and attack to make this sort of diether. Okay, and this is what's called an acetal. Okay, these are incredibly important, and as we'll see in a second, in biology. So like that. And so, for an example, right? Okay, plus OH like that. So we're going to have an excess of this. We usually dump in, like, use this as a solvent. Okay, you have a little bit of acid, right? So what ends up happening, right, that attacks there, but it does it twice, right? And so you end up with O like that plus H2O. Okay, so these hydrogens here become those hydrogens. This oxygen here becomes that oxygen there. Okay, this stuff like that. And the reason why this is important is because if, let's say, you had this compound and you hit this with dibol, you could say, and you want to take this compound to this compound, it's going to be difficult to do it directly, because if you hit it with dibol, you're going to reduce both of these. You're going to reduce it to this to OH and this to aldehyde. Okay? So what you end up having to do is we want to keep this alone. And so what you have to do is you have to protect it. And so instead, you have to protect it as an acetal, right? To make it into ether, right? Ethers are used as solvents, right? So they're incredibly reactive, right? So let me draw this in red so it's easier to see. An H plus. So what ends up happening is you end up, because your ketone is going to be more reactive than your ester, you end up protecting this as OCH3. OCH3. Okay? Then you do the dibol. Oop. Ends up being an H, right? And then you reverse this to unmask it by just dumping in water and acid, and then going and then releasing that. So now you've come here. And so this is what's called, we're not going to deal with this much, but this is what's called a protecting group strategy. If you only want to react here, but this is more reactive, what you end up having to do is you end up having to mask this part here, do the chemistry, and then unmask it to get it back. Okay, so this is classic what's called protecting group chemistry. Protecting group. Protecting groups. Okay. You also see acetals and hemiacetals in carbohydrates, right? So you have an aldehyde or a ketone. You have lots of alcohols. This can come in and do an internal, make an internal hemiacetal. So here's your acetal, hemiacetal here, right? So this comes in and attacks to make an OH plus what attacked it. It just so happens to be tethered to within the molecule. Okay, so next up, carbon-carbon bond. Again, we're talking about carbon-carbon bond formation. So here, we're going to make what's called an ylide, and stuff like that. And so all this is a nice way of having a CH2 group, okay, or excuse me, an activated carbon, okay. And so this is a nice way here, right? So you take triphenylphosphine, stuff like that, and you add whatever carbon group you want, and then add a little bit of base, and then you make that. But the nice thing is, okay, so if you were to do this directly, so if you take just a normal Grignard, because you think, oh, well, that's just like a Grignard. If you were to do that, what you would end up with is you would probably end up as a, if you know, unless you did under elimination conditions, you would end up with what is it? The mixtures of this and this. Okay, but if you did the ylide, all that happens is where the way that this chemistry goes is where this this triphenylphosphine is attached. That comes in and replaces the oxygen here, leaving the double bond intact. Okay, just like with the nitrogen, right? It left that with the primary amine, right? It left that double bond intact, and you ended up with the right. So if you had right, so if you had this and you had a CH3 NH2, right? So you would leave that, right? Because there's two carbon-nitrogen bonds working at that. You would get that. The same happens with the ylide, right? So the triphenylphosphine, right? So CH, nice. Where this carbon group is, this carbon is going to replace that oxygen there. Okay, so you're going to end up with, right? Oh, CH2. We're going to say the CH3. Okay, so it's going to be CH3. You get a direct replacement of this oxygen with whatever group is hanging off of the triphenylphosphine. Okay, it's a nice reaction to leave that double bond behind, and so you can do further chemistry. Okay, and so here we go. Predict the products. Okay, where this phosphine is attached, that guy there is going to displace that oxygen. Okay, so you're going to end up with, right, CH2, CH3. Okay, you're going to get direct displacement of that. Okay, so if you have this one, doesn't matter if it's an aldehyde or a ketone, plus CH, where that everything else goes along for the ride, right? So where that phosphine is attached, that directly replaces that oxygen. So you end up with CH benzene. Okay, Okay. There you go. Oh, I don't know why. Oh, yeah, so. Alright, so you get that, you get that. You get direct attachment of this for that oxygen. Okay. There you go. Now, biology does this. Okay, so biological applications of this. So if you have something like NADH, okay, stuff like that, so this is just a biological source of hydride. Okay, this is just basically a biological sodium borohydride. It just has a lot of extra stuff on it. Okay, but it does the exact same thing, right? So it transfers a hydrogen to that C double bond O, and you end up with an OH plus what attacked it. That's all this is. It's the exact same chemistry. Mother Nature just takes advantage of this chemistry. Okay. Okay. So for last topic. Okay, so it turns out if you get these, it's easier to see in here, right? So for most, right? So we've been harping on this thing the entire time, right? So the nucleophile attacks the C double bond O, and then that comes up. You think the alcohol plus where it attacked it. Turns out it's a little more complicated than that if you're in conjugation. And so conjugation meaning this, where you have C double bond O, C like this, right? So you have this. Right, so we have this double, single, double effect. Okay, so instead of attacking there, a nucleophile actually, it turns out, attacks there, because of course it does. Okay, it actually does attack. I'm sorry, it does attack there. Okay, to make. See the nucleophile like that. So a hydrogen ends up here. Okay. Okay. So here's the easiest way to see it. Okay. HCl. So if you're going to add this, right? So that's going to attack there, push that up. So you're going to end up with OH plus Cl. Okay. The difference is if this compound. If there's a double bond, right, so you notice how it's double, single, double, like that. That exact same reaction, now it's going to attack down there. And so you're going to end up with, you're still going to leave that ketone behind, but now the chlorine ends up there. Okay? Same thing happens with the, now this is one of the things you have to be really careful of. With amines, okay, so you have methylamine, right? So 2 nitrogen-hydrogen bonds, so you're going to get those there. Right, so you're going to end up with that. But if it's in conjugation, it acts like every other nucleophile, and it ends up going down here. Like that. Okay. Water, again, it's the same thing, right? So water, if it's a regular ketone, it's going to go there. If it's a conjugated ketone, it's going to go down there. Now, organocopper, just go ahead and skip it, but it would put it there. Okay. Now, for the spectroscopy stuff, this is just as a reminder. So the right, you're going to have this aldehydes and ketones peaks, right? Those are going to be fairly, at this right around 1730s or the 1700s. But that's so those are going to pop up, stuff like that. And for the spectroscopy or for NMR, right? The aldehydes for the hydrogen NMR are very, very distinct because they're in the sort of 9.5 to 10 range. That's the only thing that shows up there. So for ketone, you're not going to have hydrogens, right? Because there's no hydrogens hanging off of those, right? You're going to have 2 carbon-carbon bonds and 2 carbon-oxygen bonds. There's no hydrogens on it. Now they're going to be distinct in the carbon-carbon region, and they're going to be sort of pushed down, stuff like that. So they're going to be pushed upfield a bit, stuff like that. But the pushed upfield a lot, I should say, stuff like that. But for NMR spectroscopy, these aldehydes pop up. They're very, very distinct way afield, stuff like that. So, okay, good luck.